24 billion kilometers from Earth, a spacecraft older than the internet just sent home a signal that shouldn't exist. It took over 22 hours to arrive. And when NASA's engineers finally decoded it, 3 of them stopped talking. Because the numbers on their screens described a region of space that isn't supposed to behave this way, a region no human instrument was ever meant to survive long enough to measure. This is the story of Voyager 1, launched in 1977, built to last 5 years, and still, decades after it left the solar system behind, telling us things that are rewriting what we thought we understood about the edge of everything. Stay with me, because the last stretch of this video is going to change how you think about what's actually empty in space. Before we get to the discovery, you need to understand what this spacecraft was never designed to do. Voyager 1 launched on September 5th, 1977, 16 days after its twin, Voyager 2. Its job was simple on paper: fly past Jupiter, fly past Saturn, take pictures, take measurements, come home with data. A 5-year mission? Maybe a little longer if the hardware held up. Nobody planned for what happened next. Bolted to the outside of the spacecraft is a golden phonograph record, sealed in a protective aluminum jacket, carrying sounds and images meant to describe Earth to whoever or whatever might ever find it. Greetings in dozens of languages, birdsong, thunder, a mother's laugh, music spanning cultures and centuries. It was assembled by a small committee of scientists and artists who, in the middle of designing a planetary flyby mission, took the time to also ask a much bigger question. If this thing outlives every civilization that built it, what's the one message worth attaching to the outside? At the time, that record was mostly a symbolic gesture, a message in a bottle tossed into a cosmic ocean so vast that the odds of it ever being found felt almost beside the point. Nobody involved in building it expected the spacecraft carrying it to still be transmitting data, let alone rewriting physics textbooks 5 decades later. The record was supposed to be the poetic part of the mission. The science was supposed to end at Saturn. After Saturn, Mission Control made a decision that would define the next half-century of space science. Instead of retiring the spacecraft, they aimed it upward, out of the plane where all the planets orbit, and let it keep going. Not toward anything, just out. For the next several decades, Voyager 1 crossed distance no human-made object had crossed before. And in August 2012, it did something that took scientists nearly a year to confirm. It left the heliosphere, the bubble of solar wind and magnetic influence that the sun projects around our entire solar system, and entered interstellar space. It became, and remains, the only spacecraft in history to send back real-time data from beyond our sun's influence. That's the setup. Here's where it gets strange. When Voyager 1 crossed into interstellar space, scientists expected the plasma around it, the charged particles that fill the space between stars, to be cold, calm, roughly uniform. That's what decades of models predicted. For a long time, though, there wasn't even a reliable way to measure it directly. The instrument built to take a direct density reading every few minutes, a plasma probe from MIT, had failed years earlier, not long after the Saturn flyby, which meant that when Voyager crossed the boundary in 2012, nobody on Earth knew it yet. There was no instrument left alive that could simply announce it. So the team had to get creative. They turned to the plasma wave instrument instead, a piece of hardware never meant to be the primary tool for this job. And in April of 2013, almost a year after the actual crossing, that instrument picked up something extraordinary, naturally occurring electron oscillations, vibrating at a very specific frequency, a frequency that could only be produced by plasma roughly 40 times denser than the plasma inside the heliosphere. That single number was the proof. It matched almost exactly what physicists had predicted the interstellar medium should look like. It took an indirect measurement, one nobody had originally planned to rely on, to confirm humanity had truly left home. Here's why that number matters. The density of interstellar space determines how far the sun's protective bubble can push back against it. If the surrounding medium behaves the way this reading suggested, the entire size and shape of the heliosphere needs to be understood differently than the clean, simple diagrams and textbooks ever showed. In other words, the boundary of home isn't a hard line, it's a negotiation, and the terms of that negotiation are still being measured, one faint signal at a time, by a single aging spacecraft, billions of kilometers past where anyone expected it to still be useful. For decades, scientists argued over the actual shape of that bubble. Some models drew it long and streaming, like a comet's tail trailing behind the sun as it moves through the galaxy. Other models drew it more compact and rounded, almost like a deflated pastry pressed flat on one side. Both pictures were built mostly on theory, because nobody had a spacecraft actually sitting at the boundary to check the math against reality. That's what makes Voyager 1's position so valuable. It isn't a telescope looking at the edge from a distance, it's physically there, taking a direct reading from inside the very structure everyone had only been guessing about. A single point of ground truth, sitting where no simulation could reach, quietly correcting decades of educated guesswork, one transmission at a time. And it isn't alone out there anymore. Not entirely. Its twin, Voyager 2, launched just over 2 weeks earlier, but sent on a slower path through the outer planets, crossed its own version of that same boundary in November of 2018. The two spacecraft crossed at different locations and different times, which means scientists effectively got two independent readings of the same boundary from two different angles, like taking a temperature reading from two different points on the same body instead of just one. The comparison surprised people too. The heliopause wasn't sitting at exactly the same distance for both spacecraft. That alone told researchers the boundary isn't a fixed shell with a single radius. It shifts and breathes and reacts to the sun's own changing activity, which means the picture Voyager 1 sends back today may already look slightly different a few years from now. And this isn't purely academic curiosity. That bubble is the reason Earth isn't constantly bombarded by the full force of galactic cosmic radiation, the high-energy particles flung across the galaxy by exploding stars and other violent events far beyond our own neighborhood. The heliosphere acts like a shield, deflecting a large share of that radiation before it ever reaches the planets inside it. Get the size, density, and shape of that shield wrong, and you get the actual level of protection wrong too, along with every model built on top of it, from spacecraft radiation exposure to the long-term habitability of the solar system itself. Now here's the part that should be impossible, and it comes down to power. Voyager 1 runs on a radioisotope thermoelectric generator, essentially a chunk of decaying plutonium converting heat into electricity. It loses a small amount of power every single year, slowly, permanently, irreversibly. NASA has had to shut down instrument after instrument over the decades, just to keep the spacecraft's heaters and transmitter alive. By any reasonable projection from the 1970s, the plasma wave science instrument that captured these interstellar readings should have gone quiet long before now. It didn't. Engineers on Earth found workarounds, rerouting power from decommissioned systems, adjusting operating temperatures, accepting more risk with each decision, just to keep this one instrument listening long enough to keep measuring a region of space nobody else can currently reach. Every one of those decisions is made against a clock that never stops. Voyager 1 is currently moving away from us at tens of thousands of miles per hour, fast enough that the distance between it and Earth grows by roughly 1 million miles every single day. At that speed, the light and radio signals carrying its data still take the better part of a full day just to arrive, and that gap will only keep widening. The spacecraft isn't simply far away. It's actively, continuously getting farther, second by second, as engineers try to keep pace with a machine that is quite literally outrunning their ability to reach it quickly. To stretch its power further, mission planners have spent years quietly switching off instruments one by one, in a deliberate order designed to preserve the ones providing the most valuable science for as long as possible. Heaters have been turned down to temperatures the original engineers assumed would damage the hardware, a risk the team accepted anyway because the alternative was losing the instrument outright. Nothing about extending this mission has been effortless. Every extra year has been earned, argued over, and paid for with some other capability, quietly switched off in exchange. And the reason that matters isn't sentimental. It's that Voyager 1 is currently the only instrument humanity has anywhere in interstellar space. If it goes dark before a successor arrives, and nothing's currently scheduled to reach interstellar space for decades, we lose our only direct sensor in this region entirely. Every reading from here forward is a reading nobody may get to replicate in our lifetimes. That's what makes every one of these discoveries so significant. Each one might be the last data point of its kind for a generation, and the spacecraft has already proven, more than once, just how close that ending can feel. In November of 2023, Voyager 1 stopped making sense. Not stopped talking. Stopped making sense. The carrier signal was still there, a faint radio hum confirming the spacecraft was alive and still pointed at Earth. But the actual data buried inside that signal, the numbers meant to describe its health, its instruments, its status, had collapsed into a single repeating pattern of ones and zeros. Gibberish, a dial tone standing in for a voice. For nearly 5 months, that's all Earth received. Engineers described it later as the scariest moment in the mission's history, worse than any prior scare, because for the first time, they genuinely didn't know if the spacecraft could be recovered at all. The problem, they eventually discovered, lived inside one of Voyager 1's 3 onboard computers, a system called the Flight Data Subsystem, whose entire job is to package the spacecraft's readings before sending them home. A single memory chip inside that system had failed. Not glitched, failed, and with it went a small slice of the software the computer needed to function, roughly 3% of its total memory, which sounds tiny until you remember that 3% of a nearly 50-year-old, impossibly cramped memory bank can be the exact 3% holding the instructions that make everything else run. There was no way to repair the chip itself. It was gone, sitting somewhere in interstellar space, permanently dead. So instead of fixing it, the team did something almost stubborn in its creativity. They rewrote the missing code and tucked the pieces into whatever spare corners of memory the computer had left, hoping the machine could still run correctly with its instructions scattered like that. Every test of that idea came with a brutal cost. A command takes around 22 and a half hours to reach the spacecraft. The confirmation that it worked takes another 22 and a half hours to come back. Every single attempt is a 2-day commitment with no partial credit. Get it wrong, and you don't find out until nearly 2 days later, and you may have used up one of a shrinking number of chances. They sent the first piece of the fix in April of 2024. A day later, the reply came back, and for the first time in 5 months, Voyager 1 sounded like itself again. It's worth sitting with what that actually means. A handful of engineers, working from documentation written for hardware that no longer exists anywhere else on Earth, using a programming approach most of them learned specifically for this one aging spacecraft, solved a problem across 24 billion kilometers using patience measured in days per attempt. Many of the people who originally designed these systems have since retired or passed away. The knowledge to keep this specific machine alive now lives in a very small number of minds, and every year that number gets smaller. So when Voyager 1 goes quiet again, and it will, there's a real chance the reason isn't drama. It's simply that nobody left knows exactly how to talk it back into working. The people who led that 2024 repair described it afterward less like an engineering job and more like an act of translation. They weren't writing new code for a modern chip with billions of transistors and effectively unlimited memory. They were editing a program written in the 1970s on a system with a tiny fraction of the storage capacity of a basic modern calculator, using notes and manuals that were themselves decades old and, in places, incomplete. Some of the original engineers who designed these exact systems had already retired by the time the problem occurred. Others had passed away. The team solving the puzzle in 2024 was, in a very real sense, having a conversation with decisions made by people who could no longer be asked directly what they meant. And there was no room for a wrong guess. Every idea had to be tested at a distance where a mistake wouldn't just fail quietly, it would cost another 2-day round trip before anyone even knew it had failed, on a spacecraft with a power budget too thin to forgive many more attempts. Imagine debugging a piece of software where every single test run takes 2 full days to return a result. On hardware you can never physically touch again, built by people who are no longer alive to answer your questions. That was the actual working condition for the team that brought Voyager 1 back from gibberish. When the fix finally landed and readable data started flowing again in April of 2024, engineers at Mission Control didn't just get a working spacecraft back. They got proof that a machine built for a 5-year planetary tour could still be reasoned with, patched and coaxed back to life across 24 billion kilometers using nothing but persistence and a very old set of blueprints. Let's go back to the discovery itself, because the story didn't end with that one 2013 signal. For years afterward, the only way scientists could measure the density of the interstellar medium was to wait for a shockwave. Occasionally, the sun itself sends out a burst of energy so massive it travels outward past the heliopause and rattles the plasma around Voyager 1, producing a brief, loud spike the instrument can detect, roughly once a year, like a storm rolling through on its own irregular schedule. But storms only tell you about the weather during the storm. They don't tell you what's happening in the calm in between. Then, digging back through years of quiet, unremarkable data collected between 2017 and 2020, researchers found something nobody had noticed before. A signal so faint it was only a few times stronger than the instrument's own background noise. Not a storm, a hush, a continuous, steady hum, present the entire time, hiding underneath every other reading. That hum let scientists do something they'd never been able to do before: measure the density of interstellar plasma continuously. Not just during the rare, loud events, but constantly, sampled every few days across a stretch of roughly 10 astronomical units. For the first time, instead of a handful of scattered data points separated by long silences, there was something closer to a continuous map. And that map revealed texture, fluctuations at the scale of a single astronomical unit, turbulence. The interstellar medium wasn't the smooth, featureless void the earliest models assumed. It had structure, and that structure varied even across relatively small distances, the kind of variation you'd expect from a fluid in motion rather than an inert vacuum. Nobody expected a 50-year-old instrument, running on a fraction of the power it once had, to be capable of hearing something that quiet. The engineers who built it in the 1970s were designing for gas giants, not for detecting a whisper of plasma turbulence 4 decades later, from a region of space that hadn't even been reached yet when the instrument left the factory. What makes that hush especially strange is that nobody is entirely sure what's producing it. The loud, storm-like oscillations have a clear cause: shock waves from the sun physically shaking the plasma as they pass through. The quiet, continuous hum doesn't have that obvious trigger. Researchers have suggested it might come from the natural thermal jostling of electrons in the interstellar plasma itself, a kind of background static built into the material rather than caused by any single event. Others have floated the idea that it could be a subtler form of quasi-thermal noise, a signature of the plasma's own internal energy, rather than an external disturbance. Nobody has fully closed the case. Think about what that actually means. A machine assembled before some of its own current mission controllers were born picked up a sound so faint it sat buried in the data for years before anyone noticed it, and that sound may be revealing a fundamental property of interstellar plasma that has never been directly measured before, anywhere, by anything. Not a discovery scientists went looking for, a discovery they found lying quietly in old data, waiting. And because that hum appears to be persistent rather than tied to rare solar storms, it opens a possibility that would have sounded absurd a decade ago, that Voyager 1 might be able to keep tracking the density of interstellar plasma continuously, for as long as its instrument and its dwindling power supply allow, without ever needing another lucky shockwave to pass by. A 50-year-old machine, quietly settling into a new kind of long-term observational role nobody designed it for, simply because it happened to still be listening when the right signal finally surfaced. Here's the part that should stay with you. Voyager 1 wasn't built to discover any of this. It was built to photograph gas giants and come home. Everything after Saturn was borrowed time, a bonus mission stitched together by engineers who refused to let a working spacecraft go quiet just because its paperwork said mission complete. And because of that decision, made almost 50 years ago, we now have the only real measurements of what lies just beyond our sun's reach. Measurements that are actively reshaping how scientists think about the size, density, and turbulence of the bubble that protects everything we've ever known. At some point, likely within the coming years, Voyager 1 will run out of power for good. One by one, its remaining instruments will be switched off to conserve the last trickle of electricity for the transmitter alone. And then, eventually, even that will go silent. Whatever it's still measuring in that final moment will be the last word we get from interstellar space until another spacecraft, one that hasn't launched yet, reaches that same edge, decades from now. That's the strange responsibility sitting on top of every reading Voyager 1 sends home right now. Not just the science itself, but the awareness that the science might stop being collected long before it stops being needed. So the real question isn't just what NASA has confirmed so far, it's what Voyager 1 is still listening for right now, in whatever time it has left, and whether we'll be ready to keep listening once it finally goes quiet. There's something worth sitting with in the fact that almost every major discovery in this story came from an instrument nobody originally planned to rely on, recorded during years nobody was actively watching, and noticed only because someone eventually went back and looked closely at data that had already been sitting on a server, unremarkable for years. The universe, at least this small corner of it, didn't announce itself. It had to be found by people willing to keep checking long after the official mission was supposed to be over. That's arguably the real through line of this entire story. Not the plutonium, not the plasma wave instrument, not even the boundary itself. It's the decision, made over and over again across 5 decades, by different teams of engineers who never expected to still be working this job, to keep listening anyway, to patch the software one more time, to reroute one more watt of power, to go back through 5-year-old data one more time, just in case something was hiding in it.